Hi everyone, welcome to this very special webinar on how to deploy IoT infrastructure in hazardous zones, which are zones where there is a risk of explosions due to presence of gas or other explosive chemicals. My name is Olivier Hersan, I'm the CEO of Actility. Actility specializes in deploying IoT infrastructure for industries in general and sensing at large scale. Today, we have several expert panelists, starting with James from Extronics. You know, the name of the company tells you all about their expertise in EX, explosive zones, and how to deploy safely electronic equipment in these specific industries. Then we'll have Thijs Borond from TWTG. They have a very vast experience monitoring critical machines, vibration monitoring, these kind of things in critical industrial environment. Then Rohit from Abiway, who has similar experience deploying asset tracking, worker tracking, also, of course, in these industrial environments where there is a risk of explosion. And we have Frank Tanquerel, who's been kind enough to present his view on introducing IoT in refineries, in petrochemical complexes. It's been quite a journey due to all the constraints there, and he has practical experience for a few years, so this will be a really invaluable testimony from Frank. For my part, I'll start quickly. I will focus on the radio aspects just to give you a feel of the difficulties that we are trying to solve. So we're talking about this kind of complex. This is a large petrochemical complex, for example, in Holland. You can see just from the picture that it's very large, first of all. There are lots of metallic buildings. You will have to monitor machines that are indoor, outdoor. If you're monitoring workers, then of course these workers will move around. You have perfect Faraday cages because every wall is metallic, but also you have a lot of high power equipment, lots of pumps, lots of motors, so a lot of parasitic RF. So all of this is a little bit of nightmare landscape from the RF engineer point of view. Now, on the other hand, these complexes, they generate us tremendous, economic activity. Lots of oil, lots of precious chemicals are being processed there. So any outage typically costs a lot. If you need to replace a pump, if you need to inspect any part of this machinery, it will cost tens of thousands of euros per hour of outage. So the potential benefit of deploying IoT, particularly for predictive maintenance type applications in this type of sites, is also extremely rewarding. So it's hard, but at the same time, it's probably among the very best ROI projects that you can have in the industry. So when approaching for the first time this type of campuses, having in mind the explosive atmosphere, the first temptation is just to shy away from it. And because LoRa stands for long range, obviously, initially, the idea is let's just stay away from the risk. Let's just deploy the gateways a little further away in an area that is not presenting any risk, like office facilities. And from there, let's reach the industrial sensors that we want to monitor. In some ways, it's true. You can do some of it, but unfortunately, it doesn't solve all the problems. Far from it. The main reasons are really threefold, and we'll detail them as we move on in the webinar. First of all, if you want to capture sensors that are inside metallic buildings, there is just no magic. Radio does not go through metallic walls, so you will need to deploy indoor gateways. That's something you will not be able to avoid. Second, something that is frequently overlooked, and we will detail it a little bit more. We are in an environment of unlicensed radio with interference, but we still want to have good QoS. And there is only one way to ensure this. It is through what's called macro diversity, having multiple receivers. So it's very important to understand, and we'll spend some time on it. The last point is, although LoRa is long range, the range depends on capacity. If you want to have high capacity sensing or very frequent sensing, you need to get closer to the antennas because the bit rate ultimately varies according to distance. So if you want to have a good capacity, many messages per second, you need to get closer to the antennas. So considering all this, it's unfortunately most of the time not possible to just ignore the EX risk, and that's why you need to deploy specific gateways, as James will explain right after me. Okay, let's give a little bit more light on microdiversity. There is a bit of math here, but it's simple to understand. On the left side, what we have represented is a situation where the radio conditions are causing a loss of about 10% of the packets. And you can see that if you compute the percentages of packets that will be lost overall on all three gateways, it's actually the cube of 10%. It's only one packet in 1,000 that will be lost on all three gateways. So although you have 10% packet lost overall in the air, having a macrodiversity, which means receiving by multiple gateways simultaneously, in that case threefold, you're able to increase your quality of service and in that case decrease the packet error rate to 0.1%. So that's absolutely essential in LoRa. The antennas in the LoRaWAN network, they collaborate, and they collaborate specifically with one purpose: to decrease the packet error rate and increase the quality of service, which is absolutely essential in any industrial deployment, particularly when you have a lot of noise, lots of parasitic RF. By contrast, and that explains why you have this momentum for LoRa, for example, versus mesh. In a mesh network, the contrary happens. If you have 10% radio packet loss on a link, after 3 hops, you will get not quite 30%, but obviously you see this multiplication of packet loss. So in a mesh architecture, the degradation of RF performance replicates in a geometric way, so it has a catastrophic impact on QoS, whereas in microdiversity-enabled star networks, you can pretty much resist interference and still provide a good quality of service, despite the local radio conditions. So that explains why you need to deploy more than one gateway. The cells need to be overlapping, and you need to have a bit more reception capacity than just one gateway. So one thing you should never do in an industrial site is deploy these autonomous gateways, with an embedded network server that don't collaborate with each other, and just put these gateways side by side in a way that forms a non-collaborative network. This obviously does not implement microdiversity, creates all sorts of other issues when sensors are seen by multiple gateways. So that's really a no-go. You need to deploy gateways coordinated by a network server. So overall, once you have these gateways in place, the network server will be responsible for coordinating the radio part. This is called the adaptive data rate in LoRaWAN. It will adapt the transmit power, the number of transmissions using several channels typically to ensure frequency diversity. It will also control the data rate, how fast the sensors are able to talk. All of this will be done under constraint of battery consumption, because obviously the goal is not to have everybody speak full blast, full power all the time. And it's a little bit subtle, actually quite complex, these types of algorithms, because you don't want the network to oscillate. You don't want to increase power for everyone, get collisions, decrease power for everyone. So the implementation of ADR is really sensitive, really key for the performance of the LoRaWAN network. One thing that's important to keep in mind is how LoRaWAN networks scale. In many of these industrial deployments in ATEX, IECEx areas, you will have a lot of sensors, and some of them will communicate quite a lot. So you will need to ensure high capacity. In LoRaWAN, you increase the capacity of a network by bringing the antennas closer to one another. So you have smaller RF cells. You can see this, the diagram on the left illustrates the capacity of a network as you get the gateways closer to one another, and you can see the capacity increases quite fast. On the right, you can see also a positive impact of macrodiversity. The curve in red shows the capacity of a network for a given distance between gateways with a single gateway covering the node. And the curve in blue is showing the same capacity if you have threefold coverage. So if you have three macro diversity covering the device. So you can see that the capacity increases a lot. So not only macro diversity gives you better QoS, but also it gives you a higher capacity in your industrial facility. So that's really the way to go, for this type of LoRaWAN deployments. So as wrapping up, the network server is the key enabler for the industrial grade performance of your network. It will manage all the uplink, it will manage the adaptive data rate, it will manage the selection of gateways when you go downlink, the scheduling of these downlinks, because you have multiple ways of sending a downlink to devices. Overall, orchestrates all the gateways that you have deployed. In the end, it makes a big difference. This was a benchmark that was made by one of our customers in Singapore. You can see that in the exact same environment, with a proper implementation, you can get to very close to zero packet loss. In their case, they were simulating mass transmission of one packet every 2 seconds by their sensors, versus a more direct implementation, particularly around the ADR, without some of the sophistication that we have implemented, which in this case leads to about 60% packet rate and a maximum transmission of one packet every 5 seconds. So all these algorithmics around controlling the RF of the devices really makes a big difference in terms of capacity, but also in terms of quality of service that you can get on your industrial premises. The last part that I want to emphasize is security. All these facilities, they are typically secure, sensitive environments. So it's very important to have strong VPNs in place, public key infrastructure in place, and typically all the gateways, they will be audited by the security departments of these factories before you're allowed to deploy them. So the main takeaway for this part, unfortunately, you will need more gateways than you think initially in these projects due to the complexity of the site and the need to deploy macro diversity. Because of this, some of these gateways, they are likely to have to be deployed in hazardous zones, and you'll get more details later on. These zones, they can be qualified as zone 0, zone 1, zone 2, and depending on the zone, you will need a different type of protection. And once the network is in place, it's really the adaptive data rate algorithm that will be responsible for the stability of the network, and that will not show in the POC phase. So be careful. You need to study this carefully. Don't conclude from a successful lab with 3 sensors that it will work at scale. Unfortunately, it's more complex than this. So LoRa is not magic, clearly, as we've explained. You still need to work around a few complexities, but still, it's really your best friend when you deploy ATEX IECEx. First of all, the infrastructure is a lot less dense than what you would get in 2.4 gigahertz frequency, so you need less gateways, and that's less expensive. But when you're a device designer, obviously, explosions, they are triggered by high temperatures, by sparks. And therefore, when you design PCBAs for ATEX IECEx devices, you're trying to avoid capacitors, you're trying to avoid coils, you're trying to limit your current as much as possible. And LoRa really makes this a lot easier because you have very, very low peak currents. The peak current in the LoRa device is about 30 milliamps. So you need smaller fuses, you need smaller capacitors. For example, compared to cellular, where you easily get peak currents around 300 milliamps or more, which require capacitors and therefore make the overall ATEX protection a lot more difficult. So with that, I leave the mic to James. We'll be talking about the gateways more particularly and how to protect them.
Thanks for that, Olivier. So hello everyone, I'm James Eastwood. I'm the product manager at Textronics, and I'll be talking to you about deploying LoRaWAN gateways in hazardous environments. So the first question to answer is why a customer couldn't put their standard equipment in the hazardous area. Simply, all equipment for use in hazardous areas needs to be suitably certified. Non-certified equipment could fault, and that could lead to a spark or an excessively hot surface on the device, which could ignite a surrounding gas or dust if present. And the whole point of certified equipment is to prevent those explosions from occurring. Now, often our clients are so focused on the technology and implementing LoRaWAN that the hazardous area is an afterthought, albeit a necessity for the client's project deployment and their digitalization roadmap. So we regularly see requests for the worst case. Let's cover all bases. And customers will ask for Zone 0, 2C, T6 as their requirements. Now, that covers all bases, but to achieve that, it'd either be impossible or very expensive. And the people that are specifying these EX parameters, they're often so involved in the technology and they're not part of the process team that would understand the hazardous area classifications that suppliers like us would need to comply to. Now, this approach of asking for the worst case scenario, it makes it that we have difficult conversations as the clients are asking for the impossible, not what they actually require. So by providing accurate information on the hazardous area means that Extronics and other suppliers can offer a solution that is most appropriate for the requirements. And doing this early in the project ensures that sufficient budget is allocated. And this, of course, contributes towards an optimized project and timely deployments. So what do we mean by a hazardous area? And simply, it's an area with a hazardous atmosphere where there is a risk of an explosion. And this could be an explosion due to flammable gases, combustible dusts, vapors, or fibers. And the simplest analogy that sort of resonates with most people is the gas station forecourt. And if you look at the image in the top right, you'll see that a zone 0 is hazardous essentially all the time. And that's what you'll get inside the fuel storage tanks and the tanker itself. A zone 1 is hazardous in normal operation, and that's quantified by about 10 to 1,000 hours per year. So you get that around the filling nozzles in a forecourt scenario. Now, a zone 2 is safe in normal operation, and so you would only get a hazardous atmosphere in fault conditions. And so you could apply that zone 2 principle to the entirety of the forecourt. In terms of compliance, there's different directives that apply. You could have ATEX, you could have IECEx. IECEx is generally accepted worldwide, or derivatives of IECEx are used worldwide. ATEX is more common in Europe, and in North America, they will use the Class Div approach. In terms of deploying LoRaWAN in hazardous areas, there's other things to consider as well. And this applies to all wireless networks. So the maximum EIRP, the radiated power of the antenna of a wireless device, has to fall within certain threshold limits, and that's based on the different gas groups of the hazardous area. So in a gas group 2A, you're allowed up to 6 watts of radiated power. In a gas group 2B, you're allowed 3.5 watts. And in gas group 2C, you're allowed 2 watts. Now, this transmit power cannot be user settable. We have to calculate based on the maximum transmit power of the device itself. Now, the calculation is shown here, and it's the maximum output power of the radio, the antenna gain, minus any losses in the RF path that you'll get with connections, attenuation on the RF cable, things like that. And there's an example below which shows how LoRaWAN gateways are generally okay. Devices like the BroWAN, the Multitech, they'll have a maximum transmit power of 27 dB. And if we allow for some losses of 0.2 dB in RF connection cables, our Isolate 501, we'll touch on that in a moment. And then if we add the 6 dB gain of the antenna, the total power at the antenna is going to be about 30 dBm, which is well within the hazardous area requirements, the limits there. Now, if you were to use a higher gain antenna, like an 8 dB antenna, and you had less losses in the cables, then you perhaps would exceed what's allowed for a 2C gas group in this scenario. But that's something that that customers should consider for their wireless deployments. And of course, Extronics can help and guide through that as well. So in terms of putting these LoRaWAN gateways in the hazardous areas, Extronics have these enclosure solutions, and the first one to show is the IWAP 107, and this is suitable for Zone 1, Zone 21 hazardous areas, as well as Class 1, Division 1 for North America. You can essentially choose any gateway that you would like. So if you've standardized on a particular vendor across the rest of your site, we can put that same gateway in our enclosed solutions. We're completely vendor agnostic in that regard. The Isolate 501 is an RF barrier that makes the RF output intrinsically safe, meaning that the output could never have enough energy in it to cause a spark. And this allows customers to use whichever antenna that they want in the hazardous area. The antenna itself doesn't need to be certified. It merely needs to be assessed as a simple passive device, simple apparatus, we call that. You could mount the IWAP 107 at a reasonable working height and mount the antennas remotely up high for greater coverage. And the enclosure itself is highly ruggedized, it's IP66. And the construction of the enclosure itself, the protection concept that we use is called explosion proof. And that means that should a fault occur on the internal equipment, that enclosure can contain that explosion and stop that flame from propagating outwards. Another benefit of the IWAP 107 is that if you have mains power available on your site, but the device itself only accepts DC, we will fit the necessary voltage converters, and the same goes for the data connection. If the device only has a copper Ethernet connection, but you want to put that on a fiber optic loop, we would fit the required media converter in the IWAP 107, and that is a standard option for our product. We also have the IWAP XM3, which has a lot of the same principles, but is certified for Zone 2 and 22 hazardous areas, as well as Class 2, Division 2 for the US and North American market. It offers the same vendor agnostic approach. It offers the same flexibility in terms of the incoming power and data connections. The benefit of the IWAP XM3 is it comes in different sizes, and so we can offer a more optimized enclosure size based on the size of the device that we're fitting inside. But again, you can use the same antennas non-certified with the IWAP XM3 to optimize your wireless deployments. Okay, so I hope that gave you a good insight into deploying LoRaWAN wireless networks in hazardous areas. Now I'm going to hand over to Tej. Thank you.
Thanks, James. I'm Thijs Bron, and today I will be giving a very short introduction on how TWTG navigates the IECEx certifications for hazardous areas. And I will also introduce some LoRaWAN use cases which our customers are currently using. So let me start by introducing myself. As I just mentioned, I'm Thijs Bron, the head of technology at TWTG. I have a background in electrical engineering, and my main responsibility at TWTG is to develop our roadmap for the coming years. We do this together with partners like Activity and Total Energies. TWTG is an IoT sensor supplier, and we have a whole range of different sensors focused towards the oil and gas industry, process industry, and chemical industry. What do we actually mean with the road towards ATEX and IECEx certifications? And for us, the most important part, how do we actually do this within a relatively small time span? So one of the important things of IoT is really to have a relatively fast development cycle, so you can keep track with the latest developments. So I think one of the most important questions we can ask at the beginning of what is actually IECEx protection, why is it important, and what kind of design goals do we actually have? One of our more important, one of our basic design goals in IECEx is which zone you're actually certifying for. You have 3 different types of zones. That's zone 0, zone 1, and zone 2. Zone 0 is the lowest zone, but it means that you have the highest risk of an explosive atmosphere. Zone 1 is a bit less risk, and zone 2 is a very minimal risk of an explosive atmosphere. All our devices are at least zone 1, and all our newest devices are zone 0. So what type of certification, what type of protection are we really using to achieve that? This is something which is called intrinsically safe design. Intrinsically safe design means that you design from the electronics part for a safe design. So it means whatever happens on the electronics, so not with the housing or anything, really on the electronics, it can never cause an explosion. You do this by ensuring in your design with protection methods that, for example, it can never heat up to above 130 Celsius. You make sure that if it sparks, the energy in the spark is not high enough to actually ignite the explosive atmosphere, and therefore really making sure that whatever happens, you cannot ignite the explosive atmosphere by designing, by having that design goal in mind and certifying it within the IECEx guidelines. So how do we actually do this? Now we actually simplify this process. The real thing what we do and what helps a lot for us to make it faster and easier to certify our whole broad range of sensors is actually modular design. By modularizing the design, we can make it easier to certify, also easier to certify for different regions. For example, our latest products, the vibration sensor, the temperature transmitter, and the pressure sensor have all a common part, which what we internally call the main PCB, which has the battery, the radio, the protection, and the microcontroller. And by keeping this always the same, we always have that same sort of main certification part where we do all the protection stuff. We have the radio certifications, you have the certification for the battery, and all we change if we go to a different variant of our product, for example, between the temperature transmitter and the vibration sensor, is an interface PCB, which is only a very small part within our product. It's relatively easy to certify, often doesn't have safety requirements or minimal safety requirements, so it's easy for us to actually switch from a vibration sensor to a temperature sensor to a pressure sensor and upcoming sensors, like for example the 420 milliamp. What we do next is we connect with an external connector to either third-party devices, like for example, excuse me, and like for example our pressure sensor or our pressure gauge, or sensors we make ourselves, for example the vibration sensor. And I have some example use cases with the vibration sensors in a couple of slides. Then I just want to mention this because it's also the certification on the radio frequencies. It's not really a lot to do with Hazardous certification, but on the certification level, this is always quite a challenge for us, because the certification is often forget that you need to do it, that you want to sell the product worldwide, but your first requirements of the start, I want to have a product for Europe, for example. But what we really do is from the design point onwards, we assume that the device will be globally certified, so we also design for a global certification and test for a global certification. And then it's only a matter of small step, basically paperwork, to have a sensor which you can use on a global level. So now over to the second part of my presentation, where I want to highlight our sensors and give some use cases for our sensors. But first start with the goal. So the goal actually of our sensors is often to end up in a dashboard somewhere, to have a digital twin or drive some AI tool or set some thresholds in Pi, for example. But for that all to work, what you really need is a lot of data. For example, you need to know, hey, is this valve closed? The vibration levels of a pump to see if it needs maintenance. You need to know the emissions, the temperature, a status of a valve, and so forth, and so onwards. What we have and where we come in is with our nail line. Our nail line is our line of IECEx certified zone 0 or zone 1, but all the devices on the left side are zone 0 certified devices for a whole range of use cases. So, for example, our vibration sensor used for cases like bearing fault detection, cavitation detection, lubrication. Then we have our temperature solutions. Our temperature solutions are really focused towards heat exchanger, steam trap monitoring, and all those monitoring, maintenance, and optimization use cases. Our pressure sensors for example, static pressures in offshore applications. Contact sensor for safety showers, if a door is open or closed, for example. And then our different range of valve position sensors, which measures the position of a valve for a quarter turn valve or a multi-turn valve, and are often used to replace a set of eyes. So now I've introduced the sensors we have, the nail line of sensors. I would like to show some example use cases of what our customers are actually doing with our sensors. So the first one is the steam trap monitoring use case. The steam trap monitoring use case is quite a relatively straightforward use case if you look at the business case around it. What you typically have if you have a refinery or a big process plant, or so, you have a lot of different steam applications, and those steam lines have steam traps on them. What often happens, they do a manual check of the steam trap, but in between, they do a manual check, for example, every couple of months, but in between, it can start leaking or blocking, and that's just a costly mistake, either fault or in the machine, which can easily be fixed by monitoring the steam trap. And by monitoring the steam trap and detecting this as fast as possible, you can reduce, for example, the amount of steam that actually leaked. And by reducing the amount of steam that actually leaked, you can reducing the amount of steam that's actually used. And by reducing the steam that's actually used, you reduce your cost because you're using less energy, and you're also reducing the impact you have on the overall environment because you're using less energy. So the second use case is a use case we did together with Total Energies. Total Energies was one of the first users and the first ones to install our vibration sensors on a larger scale. And one of the first things they actually want to find out is if the lubrication schemes on their assets were correct, because the maintenance department suspected some issues in lubrication of some machines. So what they did is they installed 50 or so of our sensors on different assets where they suspected some lubrication errors. After installation of our sensors, they check the spectrum, so they enable the spectrum on the device, did a visual inspection of the spectrum, and you can see a large sort of bump at the end of the spectrum, which can be a clear indication of metal-to-metal wear, which can be an indication of over or under lubrication. So what they actually did is they sent out a mechanic into the field. The mechanic corrected the lubrication scheme, and after the correction of the lubrication, they did another spectrum, and here you can clearly see at the end it completely disappeared, which means that you cannot only see that you had an issue with your lubrication, but you can also see that the corrective action you actually took has the desired effect. So you can see the cause, but you can also check if the fix you make actually succeeded. In this case, it completely disappeared. So now the lubrication is done correctly, and with this, they can correct the lubrication scheme. And with this corrected lubrication scheme, they can make sure that this happens as less as possible, and therefore increasing the lifetime of. So this was the end of my presentation. Thanks everybody for listening, and over to you, Rohit.
Thanks, Thies, for a great presentation. Hi everyone, my name is Rohit and I work in Activity as a product manager for ThinkPath Location and ABB products. As discussed by other speakers, the LoRaWAN technology has created another segment of the tracking market. Indoor-outdoor tracking, focusing on campuses, industrial mining sites, closed-loop logistics, as opposed to nationwide logistics applications. Many of these sites, like petrochemical plants, have hazardous zones that require ATEX IECEx certified products. I want to start by giving a brief overview of our existing products and then go over their ATEX IECEx certifications. On the top left, we have industrial tracker with a 19 ampere hour non-rechargeable battery, and it has the largest battery lifetime. It has hardened casing, which is very suitable for use in rough environments, for example, tracking heavy objects. On the bottom left, we have compact tracker that is suitable for tracking heavy equipment. It's very similar to industrial tracker. It has a very hardened casing and comes with 3 times AA replaceable batteries and has IP68 waterproof enclosure. This tracker is certified for ATEX IECEx Zone 0 and ATEX Zone 2. I'll go over these certifications in the next slides. On the top right, we have micro tracker, which is most suitable for tracking small objects, pets, and comes with a rechargeable battery, has a buzzer, tricolor LED, and multi-mode button. And on the bottom right, we have smart badge, which can be worn as a badge around the neck and is most suitable for people tracking. It also has a placeholder to store the company badge and is certified for ATEX Zone 2, and ATEX Zone 1 certification is due in Q1 2024. I go over a few of the salient features of ATEX IECEx products in a little bit more detail. So here's a brief overview of compact tracker. This is very useful for tracking heavy equipment, as I said before, and it includes multi-technology geolocation combining GPS, ABB proprietary LPGPS, Wi-Fi sniffer, and Bluetooth. It is certified for ATEX IECEx Zone 0 for gas and Zone 20 for dust. It is also certified for ATEX IECEx Zone 2 for gas and Zone 22 for dust. And you can find on this page the marketplace ordering link, which will lead you also to the technical specifications of the tracker. In this slide, we want to introduce you the new product that we have recently launched. It's called Industrial Manageable ATEX Beacon. There's a high demand for indoor geolocation using Bluetooth, especially in oil and gas, petrochemical plants, and these hazardous areas, which actually require you to put ATEX IECEx compliant beacons in the site. And with that need, we have launched this new product, which allows you to use ABB devices as managed beacons. One of the main features of this product is that these beacons can actually be remotely configured over LoRaWAN or using ABB tracking app over Bluetooth. It has the same form factor as that of compact tracker and can broadcast popular beaconing formats like Eddystone, Alt Beacon, iBeacon, and Coupa. If you use Coupa beaconing, it requires Coupa infrastructure, and you can have an accuracy right down to 1 meter using Coupa infrastructure. The other key features of this product are temperature and battery level monitoring, waterproof enclosure, which is IP68, BLE beacon range of about 100 meters in free space, and modular fixation. In the next slide, I give you an overview of a smart badge, which is very useful for people tracking, and it can be worn around the neck with a lanyard. It has a placeholder for storing the badge, and the real application for this product is to track workers, employees for their safety, and also the monitoring of employees in different work zones. It carries 1.3 ampere hour rechargeable battery, and it has already ATEX Zone 2 22 certification, and we are also planning ATEX Zone 121, which is due in Q1 2024. Then we have Combo LPWAN Compact Tracker. This is also a new product that combines LoRaWAN and cellular IoT like LTM and NB-IoT in a single product, which allows you to use a combination of these two technologies depending on the needs of the application to increase the coverage of the tracker very significantly. This product uses Abibe Murata co-developed geolocation module, 1WL, and it includes Semtech LR1110, MT3333 MediaTek chipset for GPS and Bluetooth. It also includes Renesas, which was Sequence before, GM02S cellular IoT module. The main use case of this product is to track objects using either of the radio technologies like NB-IoT, LTM, or LoRaWAN, and is really useful for tracking heavy objects. The ATEX certification of this product is in progress and is planned for next year. Finally, the new product that we have launched recently is called LoRaWAN Relay. This also is based on a Abibe Murata geolocation module. It is very useful to extend the LoRaWAN coverage in hard-to-reach areas without deploying additional infrastructure, thus reducing the total cost of ownership for our customers. And this product also has the same form factor as that of Compact Tracker. It has modular fixation and hardened casing for waterproof enclosure and shocks, and carries 3 times double replaceable batteries. I also want to take this opportunity in this webinar to discuss ThinkPath Location, which is a service that combines location data from GPS, LPGPS, Wi-Fi, and Bluetooth. It comes with Abibe Device Manager and can be used to troubleshoot Abibe devices. ThinkPath Location is fully driven by APIs and is already integrated with popular Wi-Fi solvers like Google and Here for indoor Wi-Fi geolocation. I also want to introduce you Abibe Mobile App, which is a consumer app, which is based on ThinkPath Location Engine, and it can be white label for customer needs. We already have a customer like rule, which is using to track lost cars. Abibe Tracking app is very useful to track your loved ones, pets, small objects using Abibe trackers, and allows interesting features such as sharing your location, notifications on geofences, history of positions, and also setting up alerts. This app allows easy tracker configuration and also firmware updates. Now here is a summary of ATEX IECEx markings for all our trackers. The typical use case, as I said, for ATEX compliant products is fixed offshore platforms, petrochemical plants, mines, flour mills, or any facility that carries hazardous gases or dust and is required by law to be using ATEX IECEx compliant devices to prevent exclusion. I also want to point out that Zone 0 certification includes certification from Zone 1 and Zone 2 for gas, and Zone 20 includes certification for Zone 21 and 22 for dust. So you can see the summary below. The ATEX Zone 0, 20, and IECEx Zone 0 is for Compact Tracker, Industrial Manageable ATEX Beacon. ATEX Zone 222 is for Micro Tracker V2, Smart Badge, Compact Tracker, Industrial Manageable ATEX Beacon. ATEX Zone 121 is for Smart Badge, and we'll have this certification for Smart Badge for ATEX Zone 1 early next year. In this slide, I want to briefly give you an overview of one of the markings for ATEX Zone 0 for Compact Tracker. So this specific marking is for ATEX Zone 020 for gas. Zone 0 is for gas, and 20 is referring to dust. So C is the first logo. This corresponds to EU CE mark. EX is a logo that you have to place before every ATEX string. 2 refers to the fact that the equipment group can be used in a non-mining application. 1 is a safety category 1. G refers to gas. EX is a marking that is referring to equipment protection. IA is intrinsic safety, which means the device is protected by intrinsic safety. 2C refers to the gas group hydrogen. T4 refers to the temperature of the surface of the components to not exceed more than 135 degrees Celsius. GA is the equipment protection level, which refers to the protection under rare failures of the equipment. This is the highest level of protection. And finally, the ambient temperature for this usage of this product, which is ATEX compliant, is from -20 to 40 degrees Celsius. Here is the same next string, which is for dust. So C refers to the marking of the logo of European Union, C standards. EX is the EX logo, equipment group 2, which is suitable for non-mining applications, safety categories 1. D refers to dust. EX is explosion protection marking. IA is intrinsic safety. 3C refers to conductive dust. T135 refers to the maximum surface of the device components to not exceed more than 135 degrees Celsius. DA is equipment protection level, which is suitable for zones 20, 21, 22, and finally the ambient temperature range, which is from -20 to 40. Due to the lack of time, I summarize here the different strings of our products, and you can find more details and explanation of these strings on this link below or clicking the QR code. And if you have any questions, please do not hesitate to reach out to me or anybody in the support team to discuss some of these things further in the call. And with that, I hand it over to Frank. Thank you.
Thanks, Rohit. So, Frank Tancrel from Total Energy OneTech, in charge of the deployment of the IoT solution inside the Total Energy company since 4 years. So, why is IoT in Total Energy? It's to be an enabler of data, because we need to do more and more analytics. And the deployment we have at this moment, it's 20 sites running with IoT solution based on LoRa network in 20 sites. And for the next 2 years, this year and next year, we will have 55 new sites deployed everywhere in the world, not limited to Europe, but to US, Africa, Middle East, and Asia. Why is the choice of LoRa? It's since 5 years. It's the necessity to have a private network with data inside the Total Energy ecosystem and not outside, with high capability for gateway to manage a lot of sensors, more than 5,000, with a high coverage, 6 kilometers at the minimum. We have a use case running at 12, 14 kilometers without problem. And it's to find a low-cost solution, agnostic, to be able to do a lot of use case, because IoT-based LoRa are not only enabler of data, it is a use case implemented which give saving and benefits. So since 4 years, we deploy inside this IoT platform a lot of sensors, classic sensor to do process, to follow process, to do monitoring or to do use case like pressure, temperature, and so on. But a lot of new sensors which are new technology, like connected padlock, global position system sensor, corrosion. Corrosion could be old system, but with wireless based LoRa sensor, it is new. And we can do some use case which was not possible before. Power monitoring device, it's new, because before we need to do a lot of job inside electrical substation, very complex to do. And seismic sensor, because we have some application to develop a lot of sensor in some location to follow the seismic level. And it's done by the IoT platform and this new sensor. So this capability to develop for each use case the good sensor with a lot of suppliers inside the ecosystem, it is the nice solution to do ASA project, but to do what we want. And often we say to site during ideation, you have a dream, we can do a reality for this dream. With this sensor catalog, We have a global LoRa infrastructure based on LoRa network server with activity and an IoT platform which is common to all sites, all branches on the company. And after we send the data issue from the platform to a landing zone, who can be a historian like Pi or some other application. We send the data where we need to use the data to give the deliverable, which can be a dashboard or analytic or something else. And in each site, we install local infrastructure based on 2 gateways to be sure to have the availability we need. And after, we use a different type of network to connect this gateway to the IoT platform, often based in network of total energy, Internet network, or we use in some cases with a cyber approach, some public network with a lot of security inside. For use case, a lot of use case, no limitation at this moment. The idea is to do more than monitoring, to have saving and benefits. For the moment, we suppress the use case to do control and safety, clearly, but we begin to give more and more data for automation and control to do optimization. We do a lot of predictive maintenance. It is the biggest use cases we have for machine monitoring, to optimize heat exchanger or for cooling. We have more than 100 use cases deployed actually, and we deploy for each use case in a lot of sites because it is a scalable use case. Detection of leakage, of production loss, a lot of carbon footprint reduction use case to reduce leakage, to do the methane tracker, to do the quantification. So we have in each domain you see on the screen, we have use case dedicated to this part. Energy efficiency with the mapping of the energy consumption, but we begin to have more and more to optimize the steam part, to optimize other network which give energy inside our asset. And all the use case we do, we deploy in each type of plant and factory we have. Could be platform, could be refinery, could be chemical plant, but could be biogas site or fabrication of battery and so on. Use case, a lot of use cases are able to be deployed everywhere because it is not agnostic, but quite agnostic use case. So one use case we will show you, it is the machine monitoring. It is 40% of platform are dedicated to follow the machine inside the company, all type of machine with vibration based on TWTG or system or other technology which give a lot of data like fast Fourier transform or spectrum analysis, which allow us to do early detection and to have heavy diagnostic. And we can anticipate problems for weeks and months according to the technology we use and the analytic we do after. A lot of saving for this type of use case. Times we avoid a lot of trip or problem on machine because we stop before to have destruction. We reduce the number of people who do the analysis on site, so a lot of saving for that too. When we save the destruction of the machine, we have time to change the machine to another machine, and we save a trip. And trip, it is a problem of price, cost, because we shut down, and we reduce the gas emission because less shutdown we have, the more we are efficient for this part. And for the curative maintenance costs, we have already defined a lot of saving based on this optimization of to detect quickly and early this type of problem. This use case is deployed everywhere in the company in a lot of sites. It is the major use case we have. And to give you an example of a type of analysis, it's simple here. It is a lubrication problem detected by, it was during the COVID isolation for people inside Total Energy. So they do analyze in a remote way at home, and it detects some problem, as you see on the screen. The first level you see, it is the problem of lubrication. he asks the control room to do the lubrication of the machine, and after you have the result. So it was done by remote way, early, avoiding problem on the machine due to they forget to do the lubrication. So as you see, LoRa capability, the good IoT sensor, the good platform, the good deliverable for end user, and you have a lot of benefits and savings. And the sensors we install are deployed everywhere in the company in all environments. All sensors are ATEX or follow the rules according ATEX will be UL certificate for US or IECEx for Asia. So it's we have, because all the catalog we have are compatible with this regulation or these norm requirements. We have integrity of sensor to be able to work in marine environment, in sea, in ocean, because we have a lot of sensor deployed on platform, FPSO and so on. So it is running. We have sensor deployed in desert, in Iraq. So there is running with a lot of sound and with high temperature. We have a specific approach to allow that, but they are running. So as you see, now we begin to have industrial IoT sensor able to be installed everywhere with companies which are working for dedicated industrial sensor. I hope that a lot of people continue to use LoRa sensor and to deploy LoRa sensor for industrial, because the more we will be this topic, less expensive it should be. Thanks to all, and back to you, Olivier.
Thanks a lot, Frank. So that's the beginning of our QA session. There was a question on the maximum distance for LoRa and link capacity. Both are linked, actually. As Frank was saying, it's fairly easy with LoRa if you're in the middle of this of a desert, for example, to get 15, 20 kilometer range in line of sight, flat environment. But typically in industrial environment, you would have a lot of obstacles, a lot of metal. So I would say that the typical range to account for in an industrial environment is more something like 400, 500, 600 meters around the antenna. But it depends a lot, first of all, on the environment, of course, how many walls, the nature of the walls. If it's metallic, of course, it's like full blocking. But also, as I tried to explain, it depends a lot on capacity. LoRa has this notion of spreading factor, which is more or less the speed of communication. If you communicate at a very, very low speed, so with very long packets, you can go very far. But then the capacity is relatively small because the packets are long, so you easily get collisions. Vice versa, if you're very close to the antenna, you can prop up the communication speed to several kilobits per second, much smaller packets. And there you can have much more density of communication. So unfortunately, there is no easy answer. You need to actually simulate, and we have the tools. We have both Excel sheets and coverage simulators that allow you to check that your capacity is enough, and of course that range is enough. On the next one, the data repetition and interference. So data repetition is particularly useful because it provides channel diversity. When you have interference in RF, it's rarely an interference on the whole spectrum. It's usually certain channels at a time. So what LoRaWAN sensors can do, if they are instructed by the network server to do so, is to repeat packets on different frequencies. So you have a lot less chance to lose these packets, and it's indeed very important for quality of service. In the comparison in the Singapore project, this was the Actility LNS, not the TTN one, against ChirpStack in that case. And what it highlights is really the role of the adaptive data rate that with the exact same LoRaWAN environment, the exact same gateways, the performance and the capacity of the network actually depends on the adaptive data rate, which is, I think, clear from the explanations we had during the webinar. And so the next one, how can RF outputs be intrinsically safe? I think this one is, I don't know, James or Thijs, if you want to take it. It's really an ATEX specific question.
It is, yeah. So I'd actually answered this in the chat, but I'll answer it for all. Thank you. So the RF outputs that use our isolate technology are made intrinsically safe by protecting against all transient faults. We protect against all, we block all DC biases on an RF line, and this means that the output cannot possibly spark because there's no voltage, and we're blocking against the transient that may occur under fault conditions. The difference with our isolate is that it doesn't use traditional voltage and current limiting circuits that you would typically find in an electronic barrier used for sensors and the like. RF is different in this way.
Okay, so I understand right that it's probably a combination of capacitors to block the DC signal and coils to short all the frequencies outside of the transmit frequency, probably something like this.
Yeah, so they're very highly tuned to perform well for RF, and essentially the devices are completely open circuit for voltages.
Okay, and see, you already answered the next one, which is availability for different bands, and I think you answered that the enclosures are available pretty much for any band, right?
That's right, yes. So depending on the band, so of course you've got 868 in Europe, 923 in Australia and the like. That'll be a function of the gateway hardware that the client would choose, and our enclosure solutions don't interfere with that, don't change that in any way. We would just give you the gateway and the functionality and feature stack that you require, but with the hazardous area certification suitable for the application.
Thanks. I think the question was directed to Thijs. Is your sensors compatible with all LoRaWAN gateways and all their variants that are not compatible with each other?
Yeah, so in general, it's compatible with all LoRaWAN gateways. I think that's one of the benefits of LoRaWAN, that it's all ecosystem, and our sensors just support the full ecosystem.
If you don't find a ready-to-go LoRaWAN sensor for some sensing need like methane, a possible strategy is to split the problem in two. You can look for example, a 420 milliamp or 010 volt sensor on one side, and then connect it to 420 milliamp LoRaWAN transmitter, and the combination of the two would provide what you want. But
Oliver,
yeah.
Can I add something? So we currently don't offer a methane sensor yet, but we do have one in development, so they can contact me if they want to be part of the testing of the sensor.
Okay. Question on relay. So relay is a very, very new technology. It was actually announced at the NVID trade show last week with showing a first interop. The idea of relay is to have a battery-powered device that can capture LoRaWAN communication in the neighborhood for up to 15 sensors, I would say, and then relay it to the main network. It was developed in context of water and gas metering, because typically in these type of environments, you covering the last 10% of meters that was very hard to reach causes an extreme increase of cost of the infrastructure. So you're trying to address these meters specifically, as opposed to developing a very, very dense infrastructure. The one thing you need to know is that the relay is actually a slight modification of the LoRaWAN stack. So right before sending the normal LoRaWAN uplink packets, you need to send a small wake-up signal on a wake-up channel that's designed to tell the relay that the packet is just about to come, and therefore wake up, listen to it. So you do need a small firmware modification to the sensors to work with the relay. I guess it will progressively come to the whole ecosystem, but today it's fairly new. But that's a really great tool for indoor coverage and hard to reach device coverage, like underground, if you don't need to cover more than a big dozen devices. Question on tools available to study the LoRaWAN coverage pre and post deployment. So indeed, we provide this together with the ThinkPark platforms. We have a number of tools, actually. Typically, you start with a pre-study. That's during financial planning phase of the project. Very often we have projects, say in Saudi Arabia, you get a big chunk of land and some big construction project there. And the question is, how much will it cost to cover that land? So you start this from Excel-based tools, where typically it's based on capacity and environment. So the inputs would be the rough terrain. Is it density? Is it a suburb? Is it just plain flat landscape? What kind of capacity do you need? How many packets per hour? And so on and so on. And then what the tool will provide is an estimate of the inter-site distance. So it will tell you roughly, to cover this terrain with these capacity requirements, you will need that many gateways per square kilometer. And that's pretty good for budgeting purposes. Then the next step is to actually place these gateways. So for this, we have a different tool, which is based on terrain simulation. By the way, these tools are extremely, they are fairly difficult to use in an accurate way. You can very easily get maps, but these maps are nonsense. They will give you results that have nothing to do with the reality. So there are two difficulties there. One is to get the correct terrain data, and it's very difficult to have data that's not just top of building. So first of all, when you get the map, and we help you with this, you need to really understand what the map is. It's not enough to just get some satellite map if you don't know if it's going to be top of building or ground. So you need to really know what is the data that you're using for the 3D terrain. Then you need calibration. So we've done extensive calibration campaigns in real-life environment to calibrate these tools. And then finally, it gives you this map where you can play around and move towers. So you know the rough density. Now the issue is to exactly place each gateway to get coverage. Then you deploy, and of course, post-deployment, there are tools for while driving and going around with sensors that will give you a map of the effective coverage, effective data rates, effective packet loss in the different parts of the factory, the construction site. Is there collision, congestion alerts or alarms? So yes, indeed, if there is a certain threshold of collisions, some overuse of channels and so on, the network server would trigger the proper alarms. You can also, in diagnostic mode, you can require the gateways to do spectrum analysis. Sometimes it's useful. You might have specific interference, something that shouldn't be sending so much RF signal on certain channels. And we've had the case, sometimes people buy stuff on the web and deploy it. And actually, many of the devices, even those that are CE certified or whatever that you buy on the web, they're actually just the most crappy RF devices. They don't conform to any RF specification. So sometimes you do have these devices that create a lot of issues, and you can track them through spectrum scanning. So I would really strongly advise to, of course, never deploy just any brand bought on the web in industrial sites, because in our experience, the so-called certifications, they are not checked by customs, and you just buy anything, really. So we just talked about ATEX certification. What about the LoRaWAN certification, radio performance? Okay, so the LoRa Alliance has a test for LoRa compliance, which is based on an automated test mode. So it does work. It does provide some insights. However, I'd recommend to also run, of course, and this is what we try to do in all these partnerships. We actually pre-build running networks, and we test in real life the devices, because test mode and real life mode are two different things, And the typical pain points are the whole booting sequence. One of the issues when you have as many sensors as Frank has, for example, in refineries, if you get some event that causes the whole network to restart, you need to make sure that all devices don't restart at the same time. So a specific point of attention is really to check the randomization of restarting for LoRaWAN devices, particularly any LoRaWAN device that relates to lighting control and these kind of things. You need to make sure that they will not synchronize restart. Thanks a lot, everyone. Have a nice day.